to boil the water. How about you have a lot of water? Then do you need more heat to boil it? Yes, you need. So you need more heat. If you have more, if you have more water, you need more heat to boil, right? That is called extensive, depending on the amount. That's called extensive property. Another example is mass, right? Mass. Let's go more practical example. You and your 5-year-old sister. Do you think both mass is same? No, it's not. That means mass is extensive property depending on the amount, right? What else? Give me a few more examples. Elizabeth. Few more examples for the extensive property. How about the density? More? Any more? Volume. Exactly. What else? So, look at the more examples for in terms of exam you need more. So, what is intensity? Depending on the type of matter. Type of matter, not the amount. This blackboard is a black, right? So, if you have a small size of blackboard, it is going to be look like black. How about if you have big amount, big size? Still it will be the same color. Being smaller or bigger, it will not change the color or quality of the black. So the blackness is going to be same. So color is a like hardness. If you have a small stone, it's going to be harder, right? Bigger stone is going to be same type of harder, right? So they are the intensive and extensive property. And so as I said, delta H enthalpy is a extensive property. So extensive property is depending on the amount of substance. Let's go. If you have, as I said, a reaction, you're heating up, and it's going to be hot. So final temperature minus initial, you're getting enthalpy. So if you, let me draw it up. So for instance, you, hold on a second. Let me draw a mark in here. I don't know how much covering. Okay. So, if you have a system, with a system you have, a reaction test tube you have. You're heating it up, or you're performing a chemical reactions going on in here, and then it is producing heat. It's removing or it's releasing heat, right? So delta H would be negative or positive. Let's say it's going to be negative because delta. So initially, when you started energy, initial heat, and final heat. So final heat is going to be less. Final energy is going to be less because it's releasing all the heat. The amount of heat it had is released. So that's called exothermic. If delta H is negative, that's called exothermic because releasing heat. It sounds like releasing heat means or producing heat means it's going to be positive. But actually the term comes from it giving off heat, it decreasing heat. It giving out, that means it's losing heat, losing energy. So it will be negative. But if a system is like that, for instance, if your reaction is absorbing heat from the surroundings, absorbing heat, that will be endo. Endo, the Greek word came from in. That means in. Energy is coming in. If energy coming in, that means it become a plus. It become a positive. Because you get more, bigger energy. Because energy is coming in the system. So that will be, so delta H would be positive. instead of negative. And how the curve would look like? If you draw a curve, let's see, let's draw both curves in next to each other. So if it is, if you draw a curve for the first one, this is the one endo. Sorry, this is the exo, this is the endo. So in exothermic property, in exo reaction, is initially was very high energy. This is the one is energy. And this energy is potential energy. How much energy you have in the system. So initially was very high because it released all the heat. Finally, after releasing, it becomes very small energy. A lot of time it is a confusing part because whenever you have the word is releasing or producing heat, you might think, hey, that means product should be this one. No, this is actually reactant. Releasing or producing, they don't keep the produced energy. They're releasing out. They're giving up. So the product would be lower in terms of energy. And this one would be reaction progress. And if this happens, reactant product will be very low energy. If you draw a curve, it will be like that. So it will be, you started from here, this is the activation energy, and this is the product energy. So for instance, this is the 10 joules energy you have in the product. And you started off 100 joules as a reactant. Can you calculate delta H? Say it.
90.
Say it.
Negative.
Negative 90. Because of negative 90, this is going to be exothermic, that means this is negative. Make sure you understand why this is become negative. I want you guys to understand very clear and conceptually that reaction progressing, it losing energy, final energy of the product is less than the reactant. On the other hand, if we have a product for endothermic, which is starting off from the 10 joules, then reaction will be like that. This is the product, so this is the reactant. So reactant started with a 10 joule and product with a 100 joule. You see? Then calculate this one, delta H for the endo. Positive 90. So that means this one producing heat. You see? So in any point you guys see any downhill, that is going to be exo. Is uphill, endo. Right? And understand that producing and absorbing heat. And of course, in the next class, we'll be calculating how you know how much energy lost, how many in different substance, different types of matter, how we calculate energy of producing, energy of releasing, or energy of absorbing. We'll be concluding the next class. In this class, we'll be learning a few more terms. So here you can see also how it is. Look at setup. Producing heat, exothermic, right? And then curve will be like a downhill. And then the activation energy. If it's endo, example I have endo ice, which is absorbing heat from the surroundings, and the curve will be uphill. So I did some modification in the PowerPoint. I'll be posting that for you. So the live example, we do cold pack, right? What happening with the cold pack? Is it exo or endo? Endo in terms of which one? In terms of other way. Ice pack, yes, you're right. Ice pack is taking heat from the hand. In terms of hand, it is exo because hand is removing heat, evolving heat, producing or giving heat to the ice pack. And the other one is exo because it's producing, releasing heat. And let's go some example to understand better with this exo and endo. In terms of exam, I want you to know exo and endo with the different types of scenario. So you have that, make sure you focus on that terms in exam. Your hand gets cold. So underline means this is going to be the system and everything else surrounding. So if it is system, your hand is system, you're feeling cold in the cold room, or remember you touch the leg of the chair. So your hand is an exo because it's releasing heat to the leg of the chair. How about the eyes? Yes. Then, oh, you know that. Water boils, going to be endo. How about the next two, last two? Water vapor? Because it itself have a lot of heat. It got heat from the heating source, now it's releasing heat. The last one is ice cream. It is endo. Because it's taking heat from the surroundings, which is room temperature. And ice cream is in the 0 degrees, so it must taking heat. And the last thing is, maybe last thing, let's see how much time we cover, is state function. State function. What is it, guys? State function is, it depends only on the initial and final, right? Do you have any state function in the board which depend on only initial and final? What is it? Do you have something in the board? I talked about that, and it could be a state function. State function is depending on the initial and final, right? So what is the live example of state function? For instance, you want to go to the NASA, right? So someone think, hey, I like to drive in the highway. Of course, many of you like. So you took highway 249, Beltway 8, then 45, straight to the NASA, right? Someone say, I'm going to walk. Let's see. Oh, too long? Oh, you don't want? Okay, maybe bike. Okay, let's go. Someone said, okay, I'll be biking. I need to lose some weight. Make sure you lose some weight, drink a lot of water. Cheap. Don't cheap, small amount, okay? That will help you boost up balance system. That will help you to reduce extra fat from our body. So, okay, of course, biking is one of the best exercise ever we do. Of course, swimming is all the best too. I love it, but life is not allowing. Too much busy here, right? Anyway, so someone say, okay, I'll be biking. Someone say, I'll be driving. Someone say, I'll take a bus. Someone say, I'll be driving. My dad has a plane. I'll be taking the plane. Go right there, right? However you go, you are going actually from Tombo to NASA. It's going to be 40 miles. It is 40 miles, no matter how you go. You might passing 50 miles. You might walking, or biking with a 70 mile, turning here and there, going this, take rest and see your friend on your way. But end up you going initial to final distance, that is 40 miles. Doesn't matter how you going, right? That's called a state function. Enthalpy is a state function. No matter how you heating, we don't know how you heating. We do want to know how you heating this chemical. Whether heat coming from the reactant, releasing heat, producing heat, or you heating up. It is releasing heat. So final and initial, that will be the enthalpy. Any other example? You know that state function. How about internal energy? Yes. We don't need to know how you releasing or how you losing energy, but initial and final, we just need to know to see the internal energy. There you go. Final minus initial. That's going to be the internal energy. And heat exchange would be Q heat. Q means Q stands for heat times work done. So this term again, is going to be the details in the thermodynamic chapter. We will talk about that in details in the chapter. In here, you just know that internal energy is Q heat times work done, and if Q is positive, that means endothermic. Q is negative, exothermic, right? So we'll be learning details in thermodynamics, and so that's maybe the last thing for the class today. Heat capacity. What is heat capacity?
How much heat it can hold.
Exactly. How much heat you need, right? How much is it is taking. So let's go back. This is like water, simple water, as you see. It is water bottle, right? So you're heating it up until boil. So or you increasing, you warm it up. So how much heat you need to increase 1 degree Celsius for the whole thing? That's called heat capacity for this water bottle or water inside in it. That's called heat capacity. The second term is molar heat capacity. Molar heat capacity is for 1 mole of water. Increase temperature 1 degree for 1 mole of water is called molar heat capacity. The last thing is specific heat capacity, which is C. Which is C, you might see in the last, in the list you see, you have the lead, you have the gold, silver, copper. Each substance have different types of heat, specific heat called specific heat capacity. 1 degree temperature you changing for 1 gram, not mole. When you get 1 mole, there will be molar heat capacity. When you increasing temperature for 1 degree for 1 gram substance, that's called molar. That's called specific heat capacity. If you call 1 mole, molar heat capacity. For a whole thing, heat capacity. You see the differences? You got it. These things. Do you think the heat capacity should be same for all of them? No, it should not be. You see, if you boil water, it's going to boil slowly. It's get warm slowly. But if you heat the gold or metal like iron, it's gonna warm up. It's gonna get hard very quickly, isn't it? So heat capacity would be different based on the ability types of matter you heat it. So every one is different. This is the water 4.8 highest heat capacity. So among the metals, water is the one highest heat capacity. It absorbs a lot of heat to boil.
4.18.
4.18, yeah. That's the high. No, heat capacity doesn't have any unit. This doesn't have direct unit. It have, you see, the heat capacity is joule per gram per degree Celsius. Because for 1 gram substance, for 1 degree Celsius, and how much heat you need? That's in joule, amount of heat you need per 1 gram, and for to increase temperature for 1 degree Celsius. So, and then second, the last formula we need to calculate. How do you know how much heat you need for a substance to heat up? Right? That's called Q. How much heat you need to increase temperature, to heat it up, how much heat you need to increase certain degree of temperature. So that is called Q equal to M C S delta T. What does delta T means? Delta means change. Change, final minus initial, right? We know for sure because we talked about delta H, delta E. So T of final minus T of initial, right? So now I have a question for you guys. Do you think we should be worried about whether centigrade or Fahrenheit or Kelvin for this heat calculation?
Yes.
Yes? Anybody have no?
Yes.
Everybody yes?
No, doesn't matter.
I think it
It's the same
matters.
difference.
Okay. Anybody have? No, doesn't matter. Anybody have? One person disagree with the whole class. Yes.
I say it doesn't matter.
Why doesn't matter?
It's going to be the same difference in
Okay. Let's go back. Let's refresh our memory. Okay. Let's refresh our memory for a minute. What we talked about that chapter 1, right? changing the temperature, right? Chapter, and then Boyle's law, Charles' law, especially Charles' law, we did that, right? Charles' law was P1 by P2. Now Charles' law was B1 by T1 equal to T2, right? We are very careful with it. One more formula we did, PV equal to nRT. Tell me, in which term, which formula I said that you dare to change temperature except Kelvin. Which one I said that? PV equal to nRT. Why? Why did I say that? We said that because two reasons. First reason is our unit is in Kelvin. Second reason is there is no variable for the T. T is not variable, so you cannot put two different temperatures. Should be two different units. Should be one unit. Here we talk about that. Make sure you don't look at it. Temperature. Centigrade, keep it as it is. Kelvin, keep it as it is, and adjust it as needed. If it is multiple choice questions, that whatever you need, you convert it to. Until that, you don't worry about it. How about in here? Josh said that it doesn't matter. Imad said that it doesn't matter.
It does matter.
It does matter?
Yes.
Okay, why it doesn't matter?
Because if it was in kelvins or Celsius, it would be the same difference from the final.
Let's go-
minusing the.
Yes,
finished.
your logic.
The specific heat capacity is in Celsius, so the temperature has to be in Celsius too.
So, specific heat capacity is it has a unit, but we do not put the unit in the calculation. You might be right, but the point is when you have the key point is when you have the variable. When you have the variable, then you don't need to change. Let me show why. Suppose you have two temperatures. One is 1 degree, one is 10 degree, right? If you take it centigrade, there will be 1 and 10. If you take it Kelvin, there will be 274 and 283. Look at the difference. T2 minus T1. Look at what is the difference? Tell me. 9. How about the other one? 9 as well. Both are the 9. So it's not making any difference. The same thing was in here. It is a variable, then you don't need to worry about it. If it's not variable, only single T, you look at it, what you need, based on the other, guys, come down, based on the other constant value. Okay? So kill your tension that, I don't know, it is Celsius, Fahrenheit, or Kelvin. Exactly. That's the key. As long as they are variable, don't worry about it. Look at the answer you have to choose. So that's all for you guys. Next class will be solving how you calculate total energy, and we'll be going over the more mechanical problems and the calorimeter. Next class.
You